Hello and welcome to this video lecture. So in this lecture, we're going to continue our discussion of differential equations, specifically linear differential equations, by discussing the linear differential operator. So you might have started to recognize a particular pattern developing as we continued to work with the assumed solution, specifically the assumed exponential form of the solution for a linear, generally time invariant differential equation. So now we're going to get one step closer to just working directly with the pattern itself, rather than having to take the pattern and tie it to a particular assumed solution. And so we're going to do this in two steps. The first step, we'll be discussing the linear differential operator that's kind of helping us understand what's going on with the pattern that you've probably already started to see. And then we'll go into a discussion of a very formal framework that also effectively relies on that same pattern, or where that same pattern is a part of that framework, let's say it that way. But then we can also see that there are other things happening within that framework as well. So we'll start with this linear differential operator framework. Again, it is a framework as well, that is a very important stepping stone to getting to the point where we can actually talk about this very formal framework. And so just a little bit of a spoiler alert, if you don't want to hear what that framework is until we get there, it's of course going to be called the Laplace transformation. But at this point, we're just going to go ahead and work with this particular framework itself. So I'll go ahead and introduce it by saying that considerable, looks like I lost my S there a little bit, considerable insight can be gleaned simply by changing the notation used to represent a differential equation. Here, I'll just shorten that down to diff EQ. So let's see what that notation looks like. So if we go ahead and define what we call a differential operator, to simply be capital D is equal to d dt. Here, I'm just using t as the independent variable. Of course, it can be whatever independent variable you're working with. And so we, instead of writing this more formal longhand differential notation, we use this other differential notation, specifically a differential operator representing that we're taking the derivative of something So here, let's go ahead and say that when we're looking at taking the derivative, we then just go ahead and write d in front of a quantity, whatever that quantity is that we want to take the derivative of. Now, it's important to recognize, though, that there is a little bit of an ambiguity associated with this notation because writing d in front of something starts to look like multiplication, and we'll soon find that we can kind of work with the rules associated with multiplication and other relatively basic operations. We can follow those rules and it still works with these linear differential operators, so that makes them very powerful in that particular regard. But we have to understand that even though the patterns in the math follow those same patterns of multiplication, etc., we need to recognize that D is an operation. So it's not multiplication. Well, even though multiplication is an operation, it is not the multiplicative operation. It is taking the derivative of something. And also, that means that D itself, since it's an operator, can't take on a particular value. Unlike when we were looking in prior lectures at the value of S associated with our assumed solution, the argument of our assumed solution, assumed exponential solution for a differential equation, that S could take on values. This D cannot take on values in and of itself. It is an operator. So it's important, I want to mention that because it's important for us to remember what this capital D really is all about, what it really represents. So let's go ahead and say that it represents, as I was just indicating, taking the derivative of that quantity. Here I'll just say its derivative. Once. So you write one capital D in front, you're taking the derivative once. Now, as I said, this capital D represents an operation, but it turns out that some of the patterns that we know and understand and appreciate from algebra also appear when we're using these differential operators. So D to the n, in our case, will simply represent of course, taking the derivative n times. So let's go ahead and apply this to a differential equation. And I hope that you will see as we discuss what's happening, that you'll see how powerful a change in notation, which generally is accompanied with a change in perspective or change in approach of how we're looking at a problem, how powerful that can truly be. And a question that I always like to ask is, when you are looking at trying to solve a problem, how do you try to solve that problem? Well, unless I, as your instructor, or if you're dealing with another class, another instructor tells you to use a particular method, in which case you're stuck. But if it's your choice, you're out in industry, you're working away, you're working through some kind of dynamic model, and you have a differential equation associated with it, what method do you choose? Because as you're going to start to see, the different methods, because these methods will help you solve differential equations and you should end up at the same answer. But the different methods have different properties associated with them. They have different advantages and they have different disadvantages, and some do a better job of representing particular things than other methods. And the other methods, and on occasion, are better than the method we're considering, in this case, the linear differential operator. So the key is, what method do you use when it's completely your choice? And the answer is quite simple. Whatever method is simplest for you to use for that particular problem, which is why, even though these different methodologies will yield the same results, we present them to you so that you will have more avenues available to solving that, or for solving that problem, so that you can choose the approach that works best for that problem and for you in solving that problem. So I hope you'll start to see that when we look at these differential operators and eventually a linear differential operator, I hope you'll start to see the power of just looking at something from a slightly different perspective, and also dealing with the notation that's the slightly different notation associated with that different perspective. So let's go ahead and apply this to a differential equation so that you can hopefully start to see the power of this perspective and this notation. So now we can say that, oops, let me go ahead and erase that, my apologies. So this can be written as, and here we're going to go ahead and stay with LTI, linear time invariant. So d squared x dt squared plus a dx dt plus bx is equal to f of t. And so using this new framework, so the differential equation, of course, could be written as, and here I'm not, because it's kind of a continuation statement, I won't use its own bullet. There we go. So if we have that differential equation, it could now be written using this new notation as d squared x plus a dx plus bx is equal to f of t. Now, because I'm using this as a stepping stone for what we're going to be discussing in the near future, in the next couple lectures, I'm going to leave the notation this way. But I do want to note that in order to be technically correct, we should have an operator associated with each occurrence of the dependent function. And so you will see in the text, and it would be more formally correct to include an I here, which is the identity operator. let's put a comma, could include an I or the identity operator, where of course I times X just returns X. That's the whole point of an identity. So could include an I or the identity operator here. But in order to reduce the shock in transitioning to our future topics, I'm not going to include that identity operator here. So understand, it could be included. It is more proper to include it. But in this particular case, I have a specific reason why I don't want to include it. Now, if you choose to, if you want to include it in how you solve the problem, and of course, when you're actually submitting your solutions, you will probably, well, I shouldn't say probably, you will certainly need to use the identity operator. But again, I'm going to intentionally omit the identity operator, again, to make the form that you're seeing here more similar, much more similar to the form that you'll be seeing in the future. Now, as I said, even though the differential operator is an operator in and of itself, I've already indicated that the differential operators follow the same patterns that we typically see in algebraic expressions. And so we can see that we end up with an X in each one of these terms. And so we would be tempted to, and it turns out that we can, because of the properties of both algebra and these linear differential, or sorry, these differential operators, haven't gotten to linear yet, we can go ahead and factor that X out. And that's because the derivative is a linear operation. And so you can start to see how this idea of being a linear operator and being and this idea of linearity keep coming back time and time again, allowing us to express things in incredibly convenient ways. Because again, they're all following essentially the same underlying patterns, all these different things of algebraic multiplication, or this idea of quote unquote multiplying a quantity by d, which represents taking the derivative of it. So hopefully you can see how these patterns are all playing out, well, are similar, but how they all play out in their own particular way. So we have these differential operators, these d's. So let's go ahead now and then define a linear differential operator. And this can be defined as. So where the differential operator d is just a perfectly general operation taking the derivative of whatever quantity, these linear differential operators are very specific to the differential equation that we're working with. So the linear differential operator, defined as L, in our particular case, is just everything up here multiplying that X. And so that would be d squared plus ad plus b would be our linear differential operator. And so then we can, of course, say that Lx is equal to f of t. I should have written a t, not an x. My apologies. Lx is equal to f of t. And that's our differential equation. And that's because we have captured all the specifics of the homogeneous form of the differential equation, right? F of t would be the non-homogeneous form. We've captured all the specifics associated with the homogeneous form in the linear differential operator, with, again, of course, the exception of the initial conditions or boundary conditions. But everything else is right there. So this, of course, then allows us, so we now have this new form of the differential equation. And we can see that since it follows, these differential operators follow the same patterns as we see with algebraic expressions, we can then work with the differential equation using these operators, or here I will say operations, using operations that involve these operators that are, again, algebraic in nature. And so you might wonder why we would be interested in a linear differential operator rather than just playing with our differential operators, our D's. Well, it turns out that grouping things into that linear differential operator gives us quite a bit of insight into what's happening, because we can then factor the linear differential operator. Here, I'll just shorten that down. And we can do that if the coefficients are constant. And so now this particular approach gives us a very interesting, or is leading to a very interesting framework, because we can start working with these differential equations in a more algebraic way rather than viewing them solely as differential equations in and of themselves, or as objects in and of themselves that have their own separate set of rules. Now we can see that with this representation, sure, we have these objects called differential equations, and they do have their own rules, but now we can express them in a notation where some of our more familiar rules from algebra start coming into play. And so that's very, very powerful, because most of us as engineers generally would rather work with algebraic expressions rather than dealing with these differential equations in and of themselves. So let's go ahead. So hopefully you're now starting to see how powerful this is. So let's go ahead and work an example, and I think anytime an engineer can go from differential equations to algebra, they're going to be more happy, or more happy, great. They're going to be happier. Let's just say it that way. Okay, so let's go ahead and work an example so we can see how all this plays out. And I do want to emphasize some things in this example. So let's go ahead and say that we want to find the response, and we're given the following differential equation. I'll write it out in long form. D squared x dt squared plus 5 dx dt plus 4x is equal to 0. And we want to go ahead and work with this particular differential equation. So, and find the solution for this particular homogeneous LTI second order diffeq. So let's go ahead and, since we're talking about differential operators, let's form the linear, and I'll shorten it down again, differential operator L. So we can see that we can express then, using differential operators, we can express that differential equation as d squared x plus 5dx plus 4x is equal to 0. And so before, we were using s's with our assumed solution, and that was how that framework, the prior framework, was, or how its development was produced or was worked through, would be a better way to say it, where we ended up getting for a second derivative an s squared. Now we're getting a d squared. So hopefully you're seeing, again, as I indicated before, that we had these patterns from our prior discussions. Now we're seeing the pattern just coming straight out in this new framework without even having to go through this idea of having an assumed solution, which was maybe a little bit contrived. It's like, well, how could you get away with assuming that solution? Worked out, of course, but it was a little bit, it felt a little bit arbitrary. But here we can now see that there's nothing arbitrary about this. We are now just defining this new or this new symbol that represents an operator, and we can just write the differential equation, and the differential equation just comes out with the same form as we had before, without having this kind of what appeared to be an arbitrary decision of choosing a form for a solution. Don't even need to get into that in this particular framework. So hopefully you can see that that's a relatively satisfying improvement over what we were doing previously. So now, again, factoring out our x, we get a d squared plus 5d plus 4, all that times x. And again, all of that is equal to 0. And we can then say that, of course, because we want the linear differential operator, and so that's just everything multiplying that x, so d squared plus 5d plus 4. And just like we did previously, but now this d is an operator rather than a parameter, we can go ahead and factor this linear differential operator. And we'll see that this idea of factoring is really quite intriguing. So we'll go ahead and factor it just like it's some kind of algebraic expression, but I think you'll see that we will interpret, or we can interpret, these terms now in very different ways, or in a very different way in this particular framework. And so it gets very interesting, and hopefully you're seeing how this is kind of exciting stuff, where we're now taking a look inside a house the house of differential equations, but we're now using a completely different window than we were before, where we had that assumed solution that gave us the development of the 3 different cases. And so, but when we're looking through that different window, we have to recognize that we have to work with everything as it exists, as we see it through that window, through that new perspective. And that is also true when we look at how we factor this, because factoring it isn't exactly the same as factoring an algebraic expression, and you'll see that in a second. So let's go ahead and note, and I know I said it, but let's actually formally capture it in your notes. D is an operator, as well as L. So I'll just say it rather than write it. So D is an operator, not a variable. So unlike before, where S could actually take on a value, right, with the characteristic equation, we could set that quadratic expression to equal to 0, and we could start finding roots. Well, things don't work quite the same way in this new space, in this new framework that we're developing. So we can say that D does not take on values itself. And so you might be thinking, well, Professor Dinsmore, oh, that's not good, because we were finding roots before of the characteristic equation, and that gave us a lot of insight into what's going on. And this looks like we are so close to being able to find roots associated with the linear differential operator, and that would allow us to just charge straightforward into finding a solution. And if you wanted to, you could say that these are the roots, but that wouldn't be technically correct. So, and you actually would end up in the same place that we ended up before. But I want to give you a bit of a more consistent explanation. So instead of, again, doing this contrived thing where we would just take this linear differential operator and set it equal to 0, when it's an operator, it operates on things, it's not 0 in and of itself, so it wouldn't make sense doing that. I want to show you where we can see how we end up in exactly the same spot viewing these as operators rather than viewing them as roots, which again is consistent with this whole development that we're working through. So let's go ahead and take a look at that. So yeah, you might be tempted to say, let's just set it equal to 0, but you have really no justification for doing that. So let's go ahead and express the linear differential operator as D plus 4 operating on D plus 1 operating on X equal to 0. Now, we can recognize that if this was our characteristic equation, we would have 2 distinct real roots. And if we set this linear differential operator equal to 0 and found the roots, yeah, we would find that they are 2 distinct real roots. But let's look at this particular form of the differential equation in the following way. So this differential equation can be satisfied by saying, okay, let's let D plus 1 operate on D plus 4 that's operating on X. So we'll let D plus 4 operate on X first. And this is equal to 0. Well, we can see that if this is 0, if this whole thing is 0, one way that we could have that whole thing being equal to 0 is if everything in the square brackets is always identically 0. So we can say then that this implies that d plus 4 operating on x is equal to 0, which then gives us dx dt when we go ahead and multiply this out. So yeah, actually, let's be a little bit more precise here. Let's fill in that step and say, okay, if I go ahead and multiply all this back out, I get d times x plus 4 times x is equal to 0, which is equal to dx dt plus 4x, which is equal to 0. Well, going ahead, and we can easily separate variables here, and we can quickly see that we get dx dt is equal to negative 4x, which leads us to dx over x is equal to negative 4 dt. And then integrating both sides, we can quickly see that we get, we'll just go ahead and go with our arrows over here. We get ln of x is equal to negative 4t plus, here we'll just go with a k prime. And then going ahead and solving for x itself, we get c1 e to the negative, and this is after we take this k prime, have it in the argument of the exponential function, add it onto the negative 4t, and then we go ahead and break it off into its own exponential function, which is just a constant. And we can quickly see that this is, of course, one of our homogeneous basis functions. Actually, it's the exponential function that's a basis, but that's okay. We can still have that constant. So that's one of our homogeneous basis functions. And then, of course, since that's a homogeneous basis function, it's always going to give us 0 when operated on by this d plus 4. And so if that's the case, then it doesn't matter what this d plus 1 is doing. Anything that operates on something that's always 0 when we're talking about these derivatives or just pure algebraic multiplication, you're going to still end up with 0. Now we can, of course, put the shoe on the other foot and say, okay, well, we had this d plus 4 and we operate on it first. Well, now let's let d plus 1 operate on x. But again, this whole thing has to be 0. And so, of course, this implies the very same thing that we were discussing before. D plus 1 times x is equal to 0, which then gives us, we multiply that out. Actually, let me put my arrow down here. That gives us a dx plus x is equal to 0, which gives us dx dt plus x. And we can go through exactly the same process that we did up here, dot, dot, dot. And of course, what are we going to end up with? We're just going to end up with x is equal to c2 e to the negative t, which of course is related to our second homogeneous basis function for the solution. Now, of course, we know that the general solution is just a linear combination. We'll get that down in just a second. But I want you to understand that even though we could have just looked at these particular quantities, and here I'm kind of overlining them rather than underlining them. When we're looking at those particular quantities, we can see that they correspond identically to the roots of the characteristic equation. But because they are an operator, we really don't want to use those quantities in the same way, or those expressions in the same way as we did for finding the roots of the characteristic equation. And we can see that we don't have to. We can actually continue to work with these as operators in and of themselves. And when we do that, we end up in exactly the same spot as working with our assumed solutions, without going outside of the framework, this operator framework that we are focusing on in this particular discussion. Now, last but not least, we have the general solution, which is x is equal to c1 e to the negative 4t plus c2 e to the negative t. Now, and so there we go. And so we can see now how these linear differential operators can help us in solving a differential equation. Now let's go ahead. But before I say that, it does help us in solving a differential equation, but I want to follow that up with, it helps us solve these differential equations, but again, looking at the problem from a considerably different perspective, now from the perspective of operators rather than the perspective of the characteristic equation and assumed solutions. So hopefully you're seeing how interesting it is that we can arrive at the same answer looking at that problem, that very same problem, in two very different ways. And so hopefully you're finding that as cool as I am. I think that's pretty fantastic that we can look at the same thing from completely different perspectives and come up with very interesting frameworks, solution frameworks that actually give us exactly the same answer, which they better. Okay, so without further delay, let's go ahead and do our quick check here. So I think you'll see that the first derivative for x is simply just going to be negative 4c1 e to the negative 4t. So I'm not going to spend a lot of time on this. I think you're getting used to doing this. That's a c2, my apologies. E to the negative t, and then x double dot is equal to a positive 16 c1 e to the negative 4t. Now this time plus c2 e to the negative t, and substituting those into the differential equation and multiplying by the appropriate constants associated with that differential equation. The second derivative, of course, has a coefficient of 1, so that just comes straight on in. The first derivative had a coefficient of 5, so I just have to multiply this whole thing by 5 times 5. Well, yeah, that's fine. And so we'll have a negative 20 c1 e to the negative 4t minus 5 c2 e to the negative t. And then last but not least, we have 4 times x. And so we get a plus 4c1 e to the negative 4t, and I'm going to squish this in, plus 4c2 e to the negative t. Oopsie, got upset with me there. My apologies. Let's see if I can slide it over. There we go. E to the negative t. Perfect. So with that, what can we see? Well, I have 16c1 e to the negative 4 plus 4c1 e to the negative 4. That's 20 on the positive side. Here's my negative 20. Sure enough, they cancel out. Here I have 1 times C2 times e to the negative t. Here I have 4 of those, so 1 plus 4 is 5, minus 5, of course, is equal to 0, and sure enough, that is our solution, our general solution for that particular differential equation. Now let's go ahead and find, again, the response for a different differential equation this time. So we'll find our response. And here we actually can leverage off of our prior discussion, and that's why I want to cover this particular example. We can leverage off of our prior discussion when this idea of differential operators and linear differential operators starts to break down a little bit. And we'll also see, not in this lecture, but in the next lecture, where it turns out that going with the characteristic equation approach, the assumed solution in the characteristic equation approach, it can also run into some problems. And interestingly enough, these differential operators don't have that same problem. And so here I want to kind of give you a little bit of a pros and cons, and this is now the con side for the linear differential operator. So just like we did before, so I don't want to hold you in suspense. So let's just go ahead and quickly form the linear differential operator, because I want to get to the interesting part of this particular problem, L. And so we can see quite quickly that we're just going to have a d squared x plus 4dx plus 4x is equal to, factoring out the x's, d squared plus 4d plus 4x. And of course, I think you can quickly see that this is just going to be d plus 2 squared times x. And of course, this is, because remember, this is still our differential equation, so that's equal to 0 for the homogeneous form of our differential equation. And so you can immediately see now that if we were dealing with our characteristic equation, we would have repeated real roots, specifically repeated real roots where the value of the root is -2. Here, though, I'm still in the process of forming the linear differential operator, so we can say then that L is equal to d plus 2 squared. Now, finding our first basis function is relatively simple. We can follow the same approach that we just ran through for the first example. So we get d plus 2 times x. Now, if you want, let's just go ahead and make it a little bit more formal. So we can represent this initially as d plus 2 operating on d plus 2x is equal to 0. So I'll include that particular step in there. And then we can go implies. So I was just going to jump straight to implies, but that's okay. Let's go ahead and put that in there. So this implies that d plus 2 times x is equal to 0. And sure enough, we can find where that works out. So going ahead and multiplying, I won't multiply the differential operator out. I'll just go ahead and give you the first order differential equation that results. And we get 0, and then going ahead and doing separation of variables. And here I'll just kind of do it relatively quickly, -2 times dt. So I won't go through all the steps because you've seen them all already. Integrating both sides and then taking the exponential function of both sides, we eventually end up with x is equal to c1 e to the negative 2t, which of course is our first homogeneous or related to our first homogeneous basis function. Now the problem here, and you're probably already seeing it cropping in, is if I reverse these two, so here I was using this d plus 2. Since they're identical twins, it's almost impossible to tell, that I'm doing one or the other. But if I went ahead and quote unquote reverse these, what would I end up with? I'd end up with exactly the same basis function, which we know isn't going to work out because we need to have independent basis functions. So you can see where this method is going to run into trouble with that. But thankfully, what do we have? We have our characteristic equation, our assumed solution and characteristic equation approach from before. And what do we know? We know that when we have repeated real roots, we can say that the form of another basis function, so the form of the solution for, here I'll say the repeated real root. And notice that this method has trouble with that. And so it's easiest for us to go back again to the characteristic, the development that focused or revolved around developing the characteristic equation. And then we can recognize that xh2 is equal to c2t e to the negative 2t. But within this framework, I'll be honest, I can't see a simple way or even a complicated way of figuring that out in this particular framework. And so you can start to see where there are certain advantages and disadvantages with each of these frameworks. And this framework has trouble with these repeated real roots for an LTI differential equation. But thankfully, because of the work we did before, we already know what we're dealing with. And so then, of course, our general solution x is equal to c1 e to the negative 2t plus c2t e to the negative 2t. And there we go. Yep. Don't know where that came from. My apologies, folks. There we go. Back in the right spot now. There we go. And let's go ahead and do our double check. And again, I won't go too long on this because I think you're already familiar with it. X dot, of course, is just going to be equal to, the first term's really easy. Second term, we have to use the product rule, of course. C2 e to the negative 2t plus negative 2, I'll put that in parentheses, C2 t e to the negative 2t. There we go. And then if I take the derivative one more time, x double dot, that's clearly going to be 4c1 e to the negative 2t. Let's just do our minus 2 c2 e to the negative 2t. And then, of course, for this particular term, we have to use the product rule again. So we're going to get negative 2 c2 e to the negative 2t. And we're going to have, of course, last but not least, bringing this negative 2 down one more time, plus 4 c2t e to the negative 2t. There we go, managed to squeeze that in there. Now, of course, we can see that we can combine these guys together into a negative 4 c2 e to the negative 2t. So let's go ahead and substitute these back into the differential equation. So what do we get? We get 4 c1 minus 4c2 plus 4c2t, all that times e to the negative 2t, right? Because every one of these terms, actually every one of the terms for all of the derivatives are going to have an e to the negative 2t. So we can just go ahead and immediately factor all those out. For the first derivative, that was multiplied by a 4. So let's go ahead and just factor out that e to the negative 2 and multiply everything by 4. So we get plus negative 8 c1 plus 4 c2 minus 8 c2t, all that times e to the negative 2t, and then for x, we just multiply that by 4 as well. That one's relatively straightforward, though. We get a 4 times c1 plus, oh, let me give myself a plus there, plus 4 times c1 plus 4 times c2t, all that times e to the negative 2t. And so we can see pretty quickly here that we have a 4 times c2 times t, a 4 times c2 times t, and so that will give us a total of 8. And we have a negative 8 right here. So sure enough, that all cancels out. Here we have a negative 4c2. Here we have a positive 4c2. So those will cancel out. And here we have a 4c1 plus a 4c1 to give us 8c1 minus 8c1. Of course, that all cancels out. And sure enough, we found our solution. So hopefully you have started to see from this discussion, and hopefully you've enjoyed this discussion because it is a very interesting one, where we can define this new framework and have the notation, this new notation associated with this new framework that allows us to actually view the differential equation and work with the linear differential operator in an algebraic way rather than looking at it as a differential equation in and of itself. And so we can play with things algebraically rather than having to go through this assumed solution and then find the characteristic equation and then work with the characteristic equation algebraically. Here we just jump straight into working with the linear differential operator algebraically without having to go through some intermediate framework to get there. And so that makes this development very powerful, this approach very powerful. But in this last example, I also showed you where it has a little bit of trouble and can actually causes some problems if the differential equation just happens to have a specific form associated with it. In our next lecture, though, we'll see where the characteristic equation approach tends to have some problems. And it turns out that our linear differential, well, in this case, let's just say differential operators, our differential operators don't fall into that same trap. And so then that allows us to jump from one method where it's like, wow, this is coming out, nothing's working, can't figure out what's happening. Okay, fine. Characteristic equation approach didn't work. Now let's go over to our linear differential operators and use that particular approach. And sure enough, everything works out just fine. So, but now I will hold you in suspense, but we will see that in our next lecture. So with that, I will call this video lecture a wrap.